So without further ado, our first presenter today is going to talk about deep neural networks and how it improves radiology performance in breast cancer screening. You've seen many people talk about this topic in the last couple of years, but Krzysztof Geras from NYU School of Medicine is one of the leaders who started doing research in this space. He has a published paper now on it. He's going to talk to you all about that today. So without further ado, give a round of applause for Krzysztof.
Hi, yeah, so I'm going to talk about my adventures with deep learning and breast cancer screening. So first, I think it's very important to understand what the right tool is for the problem. And in general, in machine learning, you can consider learning tasks on these two axes, right? So one axis is how difficult it is in some intuitive human way, and the other axis is how much data we have for it. And for example, if we have very little data and we have a very difficult task, then there's no point in even trying, right? Because we're not going to learn anything with any method. If we have a lot of data for a simple task, then, or we have a lot of data in general, then maybe we can often well, if we have a lot of data and a simple task, then we probably can use something like logistic regression, right? But if we have a lot of data and we have a difficult task, then this is the kind of space in this diagram where deep learning works well, and we've seen before very successful applications of deep learning of this kind, like if you've heard of all these advances in game playing, NLP, speech recognition, and machine translation, right? So these are kind of all things that really deep learning really nails. And I think medical image analysis is this other field where deep learning is beginning to be successful. So that's why I think this is kind of the right tool for this problem. And the other perspective on this is from a very famous scientist called Richard Hamming, who is one of my personal scientific heroes, who has made this amazing talk many years ago called You and Your Research. And Hamming argues that it's very important to pick the right research questions, right? So for example, again, you can look at these kind of research questions on this axis of how difficult they are. And some questions are really too hard, right? So for example, teleportation and time travel are not the questions that we have an attack on, right? So I could work on this, but I'm probably not going to make any progress in the next 50 years. So it's maybe not the best research question. On the other hand, some questions are kind of solved, right? Like construction of a steam engine or a phone or a television. So there's not very much I can improve in there, right? So the right kind of problems to work on are on this boundary between engineering and science. And deep learning and medical image analysis are both in this kind of boundary where we can ask good scientific questions, but we have engineering tools to actually solve them. So going deeper, breast cancer screening is one of these problems. So there's a lot of breast cancer screening exams performed every year. It's about 40 million in the US. About 250,000 of these women are diagnosed with cancer, and then about 40,000 of them, unfortunately, lose their life to cancer. So it's a very important, it's a problem of a very broad impact in society, potentially, if we can do something about it. The way this cancer diagnosis is actually done is pretty complicated. So first, when someone is asymptomatic, they go to have this breast cancer screening exam. It's called screening mammography. And then what could happen is either the radiologist will conclude that they have no cancer, or they will conclude that this person needs some further imaging. So this further imaging could be in the form of ultrasound, diagnostic mammography. Later, if it's still inconclusive, it could be MRI. And then finally, if even MRI is inconclusive, then it's necessary to do a biopsy and then do a pathology exam of this biopsy tissue. And finally, after that, we can conclude whether this person didn't have cancer or this person had some malignant change or some benign change, right? So there's also a kind of a wide variety of changes which might look like cancer in these imaging modalities, but are totally benign. And what I'm going to talk about is just this part, right? So what we are trying to do is we're trying to look at just screening mammography, and then based on these 4 images, we're trying to conclude whether this person has nothing at all, or maybe has some benign or malignant change. In the hope that maybe we can avoid all of this additional imaging, or we can catch some cancers that otherwise would be missed. So this is what these images look like. They have some names. They're very high resolution. So all of these images are approximately 2,000 by 3,000 pixels. And it's very important that actually they are in this high resolution, or otherwise the radiologists would not be able to make a diagnosis, because often the cancers are very tiny. Okay, so the way we actually formulate it as a learning task is we take these 4 images, we have some learning model, I'm referring to it abstractly, and then we have 4 prediction tasks, right? So we have 2 prediction tasks for predicting the malignant changes. So one task for the left breast and one task for the right breast. And then we also predict these benign changes as a kind of auxiliary target. So even though in practice, we don't really care so much about predicting these benign changes, we can use them to regularize this learning model. So it's like maybe you have heard of multitask learning. That's this kind of idea, but we have some, maybe we care only about one task, but we have so many kind of auxiliary tasks that will help us to learn this task that we actually care about. So that's going to be the framework that we're going to be using. Okay, so but then the thing is that I think everybody has heard of PyTorch here in this room, and you know that ImageNet is kind of solved, and so if everything was solved about deep learning and and computer vision, then that would be the end of my talk, right? Because I would just download PyTorch, run it, and everything will be done. But unfortunately, this is much harder for medical image data, and especially here. So first of all, there's no public data, right? So this is the size of the ImageNet dataset, the famous dataset that it's kind of was the cornerstone of modern computer vision and machine learning. It's 40 million images, but now DDSM is the public dataset that exists for screening mammography, right? It's only 10,000 images. So of course, okay, you can. I mean, it's still good for some initial experiments, but you cannot really hope that you're going to solve this problem with so few data. So the first thing that we had to do to even think about solving this is we actually we created our own data set at NYU, because NYU has a large medical school, so we have a lot of data, and I myself actually spent maybe half a year cleaning this data set, loading it. It's a lot of work. Like even now when I think about it, I get a headache. I don't know how I managed to endure this, but somehow I did. Okay, so this part we solved to some extent. So we have so our data set has about 220,000 exams from 140,000 patients. Is over 1 million images, because some images are duplicated, and each image is at least this size, right? So these are really large images. Large majority of these images are negative without pathology, so the doctors concluded that there's nothing suspicious, and the person is healthy. About 0.5% of these exams actually contain a malignancy, and there's some fraction of them that contain a benign change. So we have 4 binary labels for each breast, because we know whether this person. Well, we know. Sorry, this is a mistake. I have 2 binary labels for each breast, right? So, so we know for each breast, we know whether there was something malignant or benign in that breast, and for the breast that had a biopsy, we also have pixel level labels that radiologists created. So they basically drew those. They basically drew these kind of ROIs retrospectively. This is okay. So this is not my paper. This is a technical report that I created just on the dataset extraction. So if you yourself are thinking about extracting some medical dataset, you should take a look at this, because it's basically because we had to discover there's actually surprisingly little on the internet about how you should pre-process medical dataset, how you should extract these labels, and basically how you should do anything about medical data. So so we created this report such that maybe people who try to do this for maybe other problems have it easier. And it's on the internet. Like it's the address where you can find it. Okay. So the second challenge of this is that those images are very high resolution, right? So this is a typical image from an ImageNet, right? It's very tiny. I don't even know what's there, but okay. But these are those medical images, right? So from our data set. So they're really big, right? It's very difficult to actually. It's going to be very difficult to process them because they are so large. And there's some really amazing property of natural images, that natural images can be rescaled to these tiny images and they don't lose so much information about. You can still determine the class if you can still determine the class of the image even if it's very small. So for example, right, like, okay, this is an image that I rescaled, like you see it's there, right? There's a tiny image, and I think probably some of you might already be able to guess what it is. What is it? Panda. Okay, yeah, okay. So yes, it is a panda, right? And and it's very important, right? You really should appreciate this. How much you can downscale this image, and you can still guess the class. And this is a very unique properties of natural images that medical images don't have, right? Like it's like if I ask you, does this person have cancer, right? There's no chance that even if you were the best radiologist in the world, you will not be able to. Even this scale images, radiologists would say they are non-diagnostic, right? They're not of sufficient quality to make a diagnosis. So we really can't. So because these images are of such a high resolution and we can't really downscale them, we have to come up with better networks that can actually process these large images without running out of memory. So we needed to design a better model. So we use something we call ResNet22, which is a modified version of. It's similar to kind of those like ResNet networks, but it's of our own design. It has fewer layers than the most powerful ResNets, and it has fewer feature maps, and it's downsampling more aggressively than those standard ResNets, except that they are downsampling in a learnable manner. So it's not just like linear interpolation, but they are actually learning to downsample. So we're not losing the information unconditionally. The network is actually learning how to downscale. And this is kind of what this network looks like. It's a pretty standard ResNet, really, at least so far. Just that it has these more aggressive downsampling. Okay, so but when we still have those pixel level labels, right? So we still have to use them somehow. And if we wanted to make these predictions with something like a UNet, then we will actually need so much memory, right? So what if we give up end-to-end training? So we created this auxiliary classifier that has a lot of capacity, and well, basically it has so much capacity, but it's not processing this entire image at once, right? So basically what it's doing is to train it, we are extracting these patches of the images and these from the segmentations by the radiologist. Each of them overlap with either with benign lesions, malignant lesions, or neither of them. And then we train it on this patch classification task, and then we apply this patch classifier kind of in a sliding window manner on those images, and we can create some additional inputs, right? So basically, this is illustrated here, maybe a little bit better. So we sample these patches, then this is an illustration. Okay, this is an animation that actually shows that how the sliding window works, but it doesn't work here. And then we have these additional it will create these kind of additional input channels for the classifier, right? So we take this image, we take the patches, we produce this patch classifier, we produce these heat maps, and then we give it back to the breast classifier. Okay, so then even though our dataset is so large, we actually have relatively few cancer examples, right? Because cancer is relatively uncommon. So we actually have to do transfer learning, and the way we did transfer learning is we have these. Well, so that's the idea of the transfer learning is that maybe you have some task for which you have a lot of data. Maybe you have maybe more labels for some task, and then you train your model on this task, and then you use the weights for the task that you're actually interested in. So even though we have only a small number of people undergo a biopsy, there's also something called screening by rats, right? So basically, when someone goes when someone has the initial assessment, they are assessed whether they don't have cancer, or maybe they have something mildly suspicious, or they have something that looks abnormal but it's not cancer, right? So these are kind of extra information. So what we did is we use these labels, these kind of initial screening labels, as is a kind of like extra task that we pre-trained the model on. So even though they are quite noisy because they depend very much on the radiologists, radiologists might not necessarily always agree on these. They're still a good task to pre-train the model on. So we trained this model on these bi-rats labels, and then we reused some parts of the model for cancer classification. Okay, so finally, the other challenge is that data has these are four images, and we have to somehow deal with the fact that there are four images and not just one. So how we can integrate the information between views is kind of an open problem in machine learning in general, right? It's like multimodal learning. It's called multimodal learning in machine learning. It's a very active area of research. It's kind of unclear how to do that. Okay, so to solve this question, it's difficult to have a very strong preference for any way of integrating this information, because we could argue differently, right? That maybe it's better to compare the two breasts for the same view, or maybe it's better to compare different views for the same breast. So what we did is we used this ResNet to generate a fixed size representation for each of these images, and then we concatenated them differently, right? So either we concatenated all views, all of these representations, and then we had another extra layer, classification layer, or we actually concatenated across breasts, across views, or we can also just not concatenate, right? So experimentally, we found that this one works best. But this is really experimental, right? Like you could argue different ways, but this is just what we found. Okay, so in conclusion, our model looks like this. So we have these four images where there are two images for each breast, and because there are two breasts, there are four of them. Then we have these additional input channels produced by this auxiliary patch level classifier. We have these four networks that extract these fixed size representation. They are pre-trained with bi-rats. There's a lot of action going in these, but they're just represented as as these boxes. But actually, most computation is actually happening in these networks. And then we average these. We do some average pooling of these representations. We concatenate them across. Well, basically, we concatenate the same views for two different breasts. We add some two fully connected layers. We make predictions for all of these four binary tasks, and then we average them, right? So that's how this network works in summary. Okay, so, and of course, this is a pretty complex training process. It actually takes about 2 weeks on 4 NVIDIA V100 GPUs. Generating the heat maps actually takes a pretty long time, and just the final step, training the breast cancer classification model, it takes about 1 day. And we use all of these standard tricks like ensembling, data augmentation, class rebalancing, etc. So I would say this is kind of reflecting. I mean, we've done this work some time ago, but of course it takes time to publish papers. So it's kind of, let's say, this work represents what we were thinking maybe 2 years ago and what we finished about a year ago, right? So this is, if we were to do this now, then maybe we would use slightly different networks and maybe would be able to train it much faster. But it's a close kind of, it's like deep learning close to the boundary of what's out there still. Okay, so now this is very cool, I think, but it's important to understand how good humans do in this task, to be able to understand whether any performance that we get is actually even interesting, right? So what we did is we did a reader study with radiologists at NYU long gone. We gave them 720 exams. So 360 of these exams were negative. They had no cancer, and 360 exams came from patients that went for a biopsy. So they were either benign or malignant, or benign and malignant. There were 14 readers. They were all board-certified radiologists except for, I think, one or two. There was one medical student and a few residents among these 14 radiologists, but large majority of them were just fully qualified radiologists. And we asked them for a prediction of probability of malignancy, right? So what it means in terms of our network is that we're not asking them to predict this whether there's something benign, because it's something a bit confusing to them, right? So this is kind of really the task that we really care about, and that's what we are asking them to assess in this reader study. Okay, so this is how well, so this is measured in AUC. So AUC is a measure of how well a classifier can distinguish between two populations. So in this case, it's a population of people who have cancer and people who don't have cancer. So for radiologists, and one in this metric is maximum. You cannot do better than one, and a half is random. So so radiologists, they reach about 0.8, but you have to remember that this is not exactly the task they're used to, right? Because they usually just only predict whether someone should go through further imaging or not. They don't exactly assess whether someone has cancer. So they can be forgiven, this number, right? It's still a strong number. But so this is an average over radiologists, right? Now our model is actually a little bit stronger, right? So it's approaching about 0.888. But now the interesting things begin. That if we actually if we take all of these 14 radiologists and let them act as a team, if we average their predictions, they outperform our model, right? But this is so even though this is a really strong performance, this would require all of these 14 radiologists, just like making their prediction for every breast, right? It's impossible in practice. So if we take individual radiologists and we average their predictions with our model, then we get something almost as strong as this ensemble of 14 radiologists, which I think is very interesting, right? Because basically we can give the power of 14 radiologists to just one radiologist by assembling this one radiologist with our model. And furthermore, if we create this this unrealistic ensemble, like we can take this ensemble of 14 radiologists, then average with our model, and then we can get something even stronger, right? So what you should conclude from here is that I think, first of all, that our model is pretty strong already, but even though it's actually, it's still quite interesting that even though our model is so much stronger than radiologists themselves, in this ensemble, this human radiologist ensemble is still stronger, right? So it's kind of like an implicit proof that radiologists have learned something different from our model, and our model has learned something different from radiologists, right? So in some sense, they are complementary. And we already know from research, in deep learning that neural networks are very good at understanding texture. Actually, they rely on texture maybe even too much. So we can. So we have some ways of interpreting these results, but it will be very interesting to understand like how they actually differ. Okay, so let's ponder this for a little bit. No, okay, okay. So how that looks like for individual radiologists now. So this is the ROC curve. These are different radiologists. And this is an average among them, and this is the precision recall curve, right? So here we would like to be there, like we would like to be there, and here we would like to be there. And you can see that there's actually quite a lot of variance among different readers, among different radiologists. But if we give each radiologist an assistant, they suddenly this variance actually shrinks a lot, right? So this is without the assistance of our tool, and this is with, right? So even the weakest, especially it's more pronounced in this ROC curve, right? That even the weakest of these radiologists actually they become, with the help of our tool, they are almost as good as those best experts, right? So they all improve, but of course the experts have less to improve. Yeah, so actually we did a little bit of further analysis of this. So we looked at, these are the areas under these curves, right? So this is the area under the ROC curve, and this is the area under the precision recall ROC curve, where we give different weighting to either our model or the radiologists, right? So 1 means that we ignore our model, and 0 means that we ignore the radiologists, right? So that's why they all collapse to 1 point in both cases, right? So the takeaway from this curve that you should is that for every radiologist, there exists in both of these metrics, there exists a lambda such that we improve them, right? So even the strongest radiologists in our, and the radiologists it's insanely competitive to become a radiologist at NYU. Even these radiologists can be improved by this tool in both metrics, which is quite remarkable. Okay, so the simple models that I've spoken about here are actually available on the internet. Right, so you can download them and you can play with them. They are on the AGPL 3.0 license. So if you do something with them, you have to again release it on the AGPL license, right? So you have to basically release whatever you do with them. But so it's not really appropriate for, if you want to use it for your startup, it's not really the right license for you. But you can, but if you want to publish a paper and publish your code, then you can use these. And and they are totally available to you. Actually, a lot of people already, are trying to use this network. Actually, I've been contacted by multiple people around the world that are testing. This algorithm on their own data, or even fine-tuning for their own data. And you can look there. It's a very well kept repository. We explained everything very carefully. Okay, so but I think it's important to understand that this is just the beginning of this research, right? So even though we have some reasonably good results, maybe we did 5% of this, right? Of this work that actually needs to be done. That's why I call this towards solving breast cancer diagnosis rather than we solved breast cancer diagnosis. So first of all, this model is reasonably accurate, but it takes relatively long to train. It's not fully differentiable, meaning that we actually need these 2 stages, right? So with this kind of patch classification stage and then this breast cancer model stage. And it's quite difficult to interpret this model's prediction, right? Because there are ways of doing this, but it's not really. It's still, I would say, it is not perfect in that sense, and it's only learning the simplest possible task, right? So it's basically learning whether this person has cancer at this specific point in time. and it's learning from a single modality. I mean, from 4 images, but it's a single imaging modality, right? So there's a lot of other more complex tasks that are possible. So we have some further work on this. So here, what I'm showing you is it's an illustration from another paper that my students worked on. Here on the left, there's an image of the breast with cancerous lesion marked retrospectively by radiologists, and these are predictions that the model is making, right? So it's actually quite accurately capable of locating cancer. So it's not just making a prediction that this person has cancer or doesn't have cancer, but it's also locating it. And this model in particular is designed in such a way. So this is the paper if you want to read it. This model is designed in such a way that it can only be accurate if it's localizing, right? So this is a very strong constraint on the model. Basically, if it's unable to localize cancer, it cannot learn. So it does localize and it's accurate. So this model is basically working in the following way. So we take this input image, we have this, what we call localization networks producing this saliency map. We just do some global pooling on this saliency map to make a prediction, to make the global prediction. But then we also take this saliency map and we extract some smaller patches from this large image, and we have attention networks weighting how important these different patches are. We make a prediction based only on these local patches, and we average the two, right? So you could think of this in a way that, you know, maybe this network at the top is serving as a kind of a network that indicates this where this prediction indicates this location of the cancer, and serves as a kind of a rough global prediction, which then we will refine with these patches, right? So it's a little bit like you're learning where to look, and then you will be looking very carefully at some specific location. That's what this network is doing. And it works very well for different cases, right? So here there's a benign lesion that this model is capable of localizing quite accurately. This is the same example for the benign lesion, and also it's working pretty well for even for these large malignant lesions, and it's capable of finding these most discriminative regions. Yeah, so we can also did some work on slightly different family of models that are even more accurate. So here we actually, you know, because it's these kind of localization-based networks are very accurate, but it's very difficult to tune them because they have so many different components and so many different auxiliary losses that it's hard to have some kind of a priori idea of how you should modify them for this task. So basically, because we didn't know, we weren't sure how to modify them, we tried many different things. So basically over this base setup of this kind of like faster RCNN type of model, we tried different things. It's not that important what they are exactly, but you know. But the interesting thing is that, you know, like basically if we create this ensemble, it's already more accurate than our previous paper, right? So it's already more accurate, and then if we create this ensemble, and then if we create an ensemble of this model with our previous model, it's even more accurate, right? So we are going to actually so this is comparable to the reader study, right? So we are going actually, so this is very accurate, right? This is like almost 0.9. So this is as accurate as the ensemble of 14 radiologists if we create this ensemble of these models, right? So I guess I would just like to highlight this because it's a really strong number. Okay, so but then there are other interesting tasks that you can do, right? So for example, you can learn from sequences of exams, right? So what we're currently doing is that, right? So what we are just like taking this exam and we're making a prediction. But we could actually take a sequence of these exams and make a prediction, right? So that's kind of gives you more information about this person. Or we could make a prediction further into the future. And that's also a very interesting task. It's a little bit harder. And we have done some initial work on predicting with prior exams, where we extended our network. We had basically we were training with the current image and the previous image, and this way we were able to incorporate this information on the information on prior exams as well. And it works a little bit better than our networks for the prediction of only using the current images. And so also what we are doing right now is just we're using this we're only using those screening images, and obviously that cannot be the optimal way to do, right? Because we should be actually able to integrate these other modalities. Like we have a lot of other data that we should be able to use in our work. So we should be able to maybe even decide what's the best modality given the modalities that we already used, and then we would hopefully be able to make much better diagnosis than we are capable of doing now. So also one thing that I think is very close to my heart is the following thing, that when you're learning machine learning, then you are always learning the following vision of the world. That say you want to do something, like want to train some kind of a network that deals with some biological data, that you should read a lot of books or maybe speak to an expert, and then like where you have this conversation, and then based on this conversation, then you use some neural network, right? So basically what it implies is that we should try to put some kind of bias in the network, such that this network is better adjusted for this task. And this is obviously a sensible way of thinking, but it's missing this other part that these networks are learning from massive amounts of data these days, right? So this network that I was talking about is learning from 1 million images. No radiologist will ever be able to look at 1 million images, right? It's impossible. So I think what we should be thinking much harder going into the future is how we can extract this knowledge from these neural networks into science, right? I think this is something that I think is, well, we don't yet have the right tools in machine learning to do this, but I expect that we're going, over the next 10 or 20 years, we're going to hear a lot about this kind of like discovery, like science discovery driven by neural networks. Anyway, that's my shot at the Nobel Prize. So in conclusion, so we have a model that is at least comparable for radiologists on this task, as we framed it in our reader study. We can use it to help radiologists if we use this model as a second reader. We have more results that improve our results even further, but there's still really a lot of room for exciting work. So I'm hoping that more people will join this, and maybe we'll make more progress over the next few years. Okay, so this is something that actually the kind of work I've learned the hard way, that actually it's only possible to do this kind of work in medicine if you have a very large number of collaborators. So these are all the people that helped me with this work. So Kyung is a professor at NYU CDS. He was my mentor when I was a postdoc. Linda is she's a radiologist. She's the clinical lead of this project. Nanwu is my PhD student. Arti is also my PhD student. Jason was my master's student, and JP was also my master's student at NYU. Now there are all of these other people who also participate in this project. This is a mixture of radiologists, machine learning students. There's even actually it was even very necessary to work with so Joe Kasnelson was a cluster manager actually, and we worked very hard to actually optimize our cluster for our data, because it took so much time to load it that it was really necessary. Okay, so thank you very much, and these are the papers that you can look at if you want to get more details about our work. Thank you.
Excellent, and we're going to open it up for Q&A. Of course, you could fill out on the Slido app under the More tab. You could do Q&A for Hub 2, or just raise your hand. I'll pass around the mic as well.
Yes, thank you. Great talk. My question is that looks like you selected bounding box-based classifiers to tackle this problem, did you think about segmentation neural networks? And my feeling is that that could do much better because you have disbalanced data sets where you have very few examples of cancer and a lot of examples. Not if you use image segmentation, then within the images that have cancer, there's a lot of more learning and signal.
Okay, so that's a very good question. So I think this is actually something that I think we should, like we as scientists, should think much harder about. So this network is you should understand this network a little bit as a network that kind of does segmentation offline. So this patch level classifier, it's a little bit like doing a segmentation, except that it's doing the segmentation kind of offline because it's difficult to do segmentation of these very large images when you have limited GPU memory, right? So, we also did try these kind of networks that you're referring to, faster RCNN type of networks. We also tried this. Like this is the other paper that I mentioned there. So we found that they work comparably well. They have very different inductive biases encoded in them. I think probably like the perfect model will be something between the two, right? Because the segmentation models are very difficult to train with for this kind of large images. So we would just need bigger GPUs, or we would need some extra tricks to distribute computation between GPUs. These kind of faster RCNN models, on the other hand, they don't have the ability to understand like they don't necessarily they make the classification based on a specific location, right? So they don't understand the entire image, right? So they both have some kind of deficiencies, and I'm basically my work right now is kind of on my work in machine learning is basically on trying to build classifiers that have properties of both, actually.
Any insight onto the gaps? Any thoughts on what the difficult examples look like? Where's the network still failing? What do these images look like? Did you get any input from the radiologists you're working with about those cases?
Sure. So we're currently working on understanding this gap. So neural networks are known to understand textures better than humans because they really understand these kind of small changes. So my guess is that this gap is coming from that, but I don't have hard evidence to support it.
So you mentioned that you're just getting started now, and that what you showed us was completed a year ago. How does this process look like for you? Do you constantly have a model that you're tweaking and changing, and constantly have something that's training or new data that's coming in that you're cleaning and so on, or does it go in bursts where you kind of do something for a few months and then move on?
Well, I think it's a mixture of all of these things that you mentioned, right? Because because I'm a professor at the university, it's a I don't know how it would be if I was working at a startup or some big company, but basically, I have to be very creative in how I do research, right? Because I have some number of PhD students that have longer term projects, but then I also sometimes I have more brain power if I get more master students. So it's so I constantly get more data. I constantly update the IRB that allows me to get more data. I have some number of PhD students who are thinking more long term about what we can do. So they kind of are more focused on machine learning methodology for these for these problems. And then I have some number of master students that I maybe only have them for like 1 year, right? So I give them some shorter project. They are very motivated to publish a paper. because they have to get into a PhD program or they have to get a job, right? So it's a basically, I have to be really creative, right? In how I manage my research team. So it's a mixture of all.
Can I squeeze in one more question? When you talked about very large inputs, have you also considered or looked at all into model parallelism to basically use the memory of multiple GPUs for one large input?
Yeah. So I do. I considered that, but I thought that would be. So I guess this is, I say, if I probably was working in a big company and I had a lot of computational power, then this is probably what I would do. And if I had a lot of engineers to code that up, because of course this is kind of a reasonable thing to do. But because I'm a scientist, I have to think of, I have to innovate on the method side so that I can publish my papers, right? So I'm trying to achieve the same effect without model parallelism. But definitely, let's say if I was in the industry, then definitely that would be like one of the first things that I would try.
So I'm a clinician, and I really share your excitement about the ability to predict early. I also want to bring up the other end.
Okay.
In thinking of the future. Are you also discussing what it means for overall outcomes? Almost every screening tool for almost every cancer we have used has not touched mortality in the long term. It doesn't save lives. So as you perfect these models, should there be a broader plan to see if it's actually making a difference?
Yeah, absolutely. So, so like I said, this is just like maybe 5%, right? Or less than 5%. So, so we have a number of more clinically focused projects at NYU right now that we are trying to understand those differences between the models and the neural networks. We're trying to understand in what particular cases this model is better than, kind of where it fails. But definitely in the longer term, I expect that this field is going to drift more into doing things like prognosis as well, rather than diagnosis, right? Because it's possibly even more important than diagnosis. It's just that diagnosis is maybe a little bit easier because there's more data, right? So, and it's easier to collect than data for prognosis. But you're absolutely right that, there's a huge gap which is difficult to bridge between kind of high AUC numbers and some kind of clinical value, right? So there's definitely something we will be going in this direction.
I think I can just so one comment and one question, please. Perhaps I can start with a comment.
Sure.
In the Panda image,
Yeah.
the question was, can you see what that is?
Yeah.
That was the Panda.
Yeah.
In the breast image, that was not the same question. You ask if you can see cancer. So probably the equivalent question would have been, is that a breast? So, or the other way around, you have gone back to the Panda and asked the question like, what color are the eyes? So actually, in that case, you fail to see that at that small scale. So that would be comparable question.
Let me answer this first, right? So, I think if you just consider a classification question, whether this person has cancer or this person doesn't have cancer, this is like asking. Basically, this is it's just like it's a binary classification. Yeah, that's the key point, right? Basically, that in natural images, the fine details don't matter so much if you are just doing classification. While in this medical imaging, whether this is going to be breast, prostate, whatever, right? This kind of the part of the image that actually influences the classification decision is very tiny, right? So that's kind of exactly what I was trying to illustrate.
Right. Regarding the question, you actually put a very nice comparison there about the ability of every individual radiologist to perform that good, and then the system in itself.
Yeah.
Obviously, the radiologist and the system see different things, and that's why they have very different performances. The question is, did you consider perhaps being in education to source this algorithm for training the radiologists in ways that they haven't, been exposed to before? Yeah,
absolutely, right? So I think, so absolutely, I think this is kind of very well aligned with kind of my dream of using neural networks for extracting science, like for extracting new scientific discoveries from these networks. And like education, of course, it's potentially a very important part of this. Like if we could educate radiologists to do better radiology because we discover something new about breast cancer, then that would be, I guess that's kind of, that's a very important discovery then.
Do you have a method of actually evaluating this? I mean, over time.
Well, so, I think this is, so I think first of all, to even start doing this, we need better methods for explanation of the prediction, right? So we are beginning to do this, but it's not really mature. But then, I guess this can be evaluated in some reader studies, right? So we could do some reader study maybe now, and then we could train them, and then we could see how well they would predict maybe in a year, right? Like when they forget those images. So I think that's doable, but it's just, let's say it's doable, but it's kind of difficult to execute.
So thank you. I think this was an exciting look at the promise we've seen so far of applying the neural networks and learning to figure out how to do screening better with breast cancer. I'm curious, are there other types of cancer or other conditions that you think, given the type of data available or the opportunities, what else might this be well applied for?
Well, I think everything that humans do, neural networks will be able to do sooner or later, right? So I think, and perhaps even the things that humans can't do, they will be able to do, right? So I think or at least they will be able to complement humans in these tasks, right? So I think I don't think there is any particular part of the body where neural networks will find it harder than others. So I think what's limiting us is so I think there are kind of two limitations in this kind of research, right? So the one limitation is the data. So breast cancer is a good thing to try with because there's a lot of breast cancer screening exams. So there are some more rare types of exams that would just be difficult to learn from because there's a smaller number of them, and in particular in the medical world it's very difficult to share data between different organizations. So in practice, basically to do something you have to have a lot of data at your organization, or it will take 10 years to assemble these data sets, right? And the other thing I think is not as much appreciated is that we just don't have the right networks for all kinds of data, right? So for example, it is already pretty hard to do this for 2D mammography, right? But then in 3D mammography, where each slice is as big as, or almost as big as this one, but we also have 50 slices, then suddenly the computational problem is much, much harder. And we have some hacks, we have some hacks to deal with this, but some kind of machine learning hacks and some kind of computational hacks to this, but this is not really a solved problem, right? So to really so I think if we really want to reach the full potential of these tools, we really still need a lot of we still need many years of kind of research in machine learning, that not even necessarily in medical imaging and machine learning, but pure machine learning research.
Excellent. We'll take one more question.
Hey, I was just curious if this is being used at NYU as a part of kind of just testing it on a regular basis. Yeah,
so we are not currently using this at NYU, but we are kind of in the process of discussing it. But I think that's kind of. But I know that other people around the world are testing it retrospectively, because the model is out there, so they're beginning. I got maybe, I don't remember how many exactly, but I got multiple. I know of multiple people around the world that basically.
They reach back out and say, hey.
Yeah, this. I have this error. Right? Help me fix it. So I think there's going to be, I think probably in a year or two, there's going to be a lot of people who have tried it and they will be able to evaluate it in their own setting. I hope they will write papers and say that, can say how it worked.
Thank you, everyone. Let's give Krzysztof a round of applause. Thank you for sharing everything on your research today.